Section 1.6, some rules for differentiation. So these rules are actually just going to be extensions of those rules that we learned a few minutes ago, which is really kind of nice. So specifically, the idea is that if you take a derivative of a constant times a function, then it's true, so k is my constant, then it's true that that's just going to be the constant times the derivative of the function. Now it seems kind of silly, but it is necessary. And so the derivative of a constant times a function is the constant times the derivative of a function, and this is specifically when we're talking about k being a constant, or just a number. Then, for sums and differences, it's really kind of nice because the derivative of sums, that is what we have on the left, is the same thing as the sum of the derivatives. And so you just have to take the derivative of the independent pieces that are being added or subtracted, and you're going to be just fine. And so the derivative of sums is the sum of the derivatives. So let's try these in practice. Let's do some more complicated derivatives. So if I want to take the derivative d dx of 12 over the cube root of x. Now, first off, just a little side note, we can rewrite 12 over the cube root of x. That's the same thing as 12 divided by x to the 1/3 power. Remember, rational exponents for radicals. Then, to get this in a nice format, I can rearrange further, and that's going to be 12 times x to the negative 1/3. Alright, so that's the derivative we're going to take. We're going to take the derivative of that thing. So, d dx of 12 times x to the negative 1/3, it's then true that this is going to be the constant times the derivative of the function, so that's 12 times the derivative of x to the negative 1/3. Then we take the derivative of x to the negative 1/3 using the general power rule. That's then 12 times, general power rule says bring that power out front, times x raised to the negative 1/3 minus 1. Let's clean it up. That's 12 times negative 1/3 times x to the negative 1/3 minus 1. Multiply by 1 in disguise, that's 3 over 3. So negative 1 minus 3 is negative 4/3. And so as far as we're concerned, that is the derivative. But let's say you wanted to clean it up and put it in that radical notation again, using the cube root instead. How can we do that? Well, a handful of things. First off, 12 times negative 1/3, that reduces, right? That's 12/3, or negative 4. And then we've got x to the negative 4/3, but because it's negative, I can put it in the denominator. Then it's x to the positive 4/3 power. Then remember that numerator of a power is a power. Denominator of a power is the root. And so this is then going to be negative 4 over either the cube root of x to the 4th or x to the 4th cube rooted. It really doesn't matter. And so x to the 4th power, cube rooted, there we are. That's our derivative. Alright, now for more complicated polynomials. If we have the derivative of 3x to the 6 plus 5x minus 7, first statement, that is the derivative of sums is the sum of the derivatives. So d dx of 3x to the 6th plus d dx of 5x minus d dx of 7. Then we use our rules for each one of these independently. So first off, I've got d dx of 3 times x to the 6th, then you can pull that constant out, right? And so that's the same thing as 3 times d dx of x to the 6th. Now, I'm being very careful here, but at some point you won't have to write out every single tiny step. Just be careful about that as you're learning. Then it's plus 5 times d dx of x minus, well, at this point we could go ahead and take the derivative of that one. The derivative of constant is 0. Well, then I've got 3 times the derivative of x to the 6th. That's going to be 3 times the derivative of x to the 6th is 6 times x to the 6 minus 1, or that's the same thing as 5 plus 5 times the derivative of x, but the derivative of x using the general power rule is just 1. And then minus 0, but I'm not going to rewrite that. Then this is 3 times 6, or 18, x to the 5th, plus 5. And so now we found our derivative. Next one, I have d dx of 7 times the square root of x. I'm going to go ahead and do this in one fell swoop. This is the derivative of 7 times x to the 1/2 power minus the derivative of, and I'm going to move this denominator to the numerator, 8 times x to the negative 3rd. Well, then we can start skipping steps if you want. The derivative of 7 times x to the 1/2, that 1/2 comes out front. That's 7 times 1/2 times x to the 1/2 minus 1. Then the derivative of 8 times x to the negative 3rd is 8 times negative 3 times x to the negative 3rd minus 1. That's then going to be 7/2. But then x to the 1/2 minus 1 is really x to the negative 1/2 minus 8, negative 8 times negative 3, that's actually going to be positive 24 times x to the negative 4th. Then to do some further cleanup, the negative powers we probably want to get rid of, and so that's going to be 7 over 2 times x to the negative 1/2, 7 over 2 times x to the positive 1/2, or 2 square roots of x, plus, well, 24 on top over x to the positive 4th. And so we found the derivative. Now here's a little bit of critical thinking question. At what ordered pairs does the function that's given have a horizontal tangent line? Now this could be one point, this could be multiple points. But how in the world could we find this? Well, let's think a moment. Horizontal tangent lines have slopes of 0. Okay, that's where we're going to start. Well, we also know that in terms of our functions, slope is really the same thing as the derivative. And so if we remember that slope and derivative mean the same thing, then what could we do? Well, we could find the derivative of the function that's given, then take that new formula that we just found, set it equal to 0, solve the equation, and then all of the x values that we find that solve the equation will actually be the x coordinates of the ordered pairs. Then we can take those x coordinates, plug them back into the function, and then we'll have every ordered pair where the function has a horizontal tangent line. Alright, so let's run through all of it. So, first things first, we need to find the derivative. So, f prime of x, that's going to be what? Well, we just need to take the derivative of all of this. Well, x cubed over 36, if you want, is the same thing as 1 over 36 times x cubed. That's not the derivative, you're just thinking about it as multiplication. Well, since that's the case, I'm just going to make this a little bit faster. That's going to be 1/36 times, bring the power out for the general power rule, 3 times x to the 3 minus 1, or 2, plus, same thing here, 2 comes out front, times x raised to the 1 over 36, minus x over 4, but the derivative of x is 1, and so this is minus 1/4. And then the derivative of a constant is 0, and so that's 0. Well, that means that f prime of x is equal to, I'm going to reduce my fractions here, x squared over 12 plus 2 over 36 reduces to 18, so it's x 18ths minus a 4th. Notice that I have a typo here, so let's correct this. Right here, x squared over 12, this should still be over 12. Let's make sure I don't have any other glaring typos. Okay, great. There we are. That's the correction, which means that this is not x 18ths 2 divided by 12, 2 over 12 becomes x over 6. So excuse my typo, there we are. Then what happens? Well then, this is the equation for slope. Well, what can we do? We're going to set it equal to 0. So 0 is equal to x squared over 12 plus x over 6 minus a fourth. Well, at this point, you could use the quadratic formula with what's given. But if I haven't shown you this trick, remember that because we have an equation, and the equation is equal to 0, I can multiply by a least common denominator, and I guarantee that we'll simplify all our fractions. So between 12, 6, and 4, what is my least common denominator? That's going to be 12. And once again, this is only okay because we have an equation. So multiply 12 both sides. 12 times 0 is 0. Distribute that 12. 12 over 12 is 1, or x squared. 12 times x over 6, that's really going to be 12 divided by 6 is 2. And then minus 12 over 4, that's going to be 3. So then I get this quadratic. If you want to use the quadratic formula, you can. But I see that this factors nicely that 0 is going to be x plus 3 times x minus 1. Double check myself. Negative 1 times positive 3 is negative 3. 3 minus 1 is positive 2. Then we get that this is, via the zero product property, 0 is equal to x plus 3. And 0 is equal to x minus 1. And so we get that x is equal to negative 3 and x is equal to positive 1. So I get two x coordinates for my ordered pairs. But that's not the ordered pairs. Well, how can I find the ordered pairs? The ordered pairs are just the points a, f of a. You just plug in that value we just found into the function and get the y coordinates. So, but remember we're going to plug it back into the original function. And so since our first x is equal to 1, then what's f of 1? Well, f of 1 is going to be 1 cubed over 36 plus 1 squared over 12 minus 1 over 4 minus 5/36. Well, that's going to be 1/36 plus 1/12 minus a fourth minus 5/36, which I get to be negative 5/18. And so the ordered pair, the first one, is 1, negative 5/18. And then let's find the second ordered pair. Plug in negative 3. That's going to be negative 3 cubed divided by 36 divided by 36 plus negative 3 squared divided by 12 minus negative 3 divided by 4 minus 5 over 36. Negative 3 cubed is negative 27 over 36 plus negative 3 squared is positive 9 over 12. Minus times minus is going to be plus 3/4 minus 5/36, which I get to be 11/18, which means that my second ordered pair is negative 3, 11/18. And so those are the two ordered pairs on that function f of x, where specifically they'll have horizontal tangent lines or flat spots. Now this is actually interesting because I may not know a lot about what this graph looks like, but I now know that at these points you're either going to have a peak, a trough, or some weird flattening spot. And so it's possible to have a flat spot right there with a tangent line. And so we learned something about our function.